Okay, here's where we were at the end of the last video. We've got these 7 species, and we've got 9 different characters. And what biologists do when they're trying to reconstruct a phylogeny is they go through and they look at all these different characters on each of these species, and they score each species for the different characters. So you go through and look at a chimpanzee. Has it got mammary glands? Check. Has it got claws and nails? Check. It's got fur. It's warm-blooded. It does not go through metamorphosis, so that's a no. Nope, no fins, no keratin scales, no gills, and no gizzard. Okay. And then you go on to crocodiles, and you take a look at the crocodile. Once you're finished, what you have is this character state matrix, which tells you the character state for each character for each species. This is what we're going to use to reconstruct the evolutionary history of this group of organisms. This is why we care about clades, is because, remember, our basic logic that we're working with is that an ancestor that evolves a novel character state will pass that novel character state to all of its descendants. What that implies is if we see a novel character state in some organisms in the present day and not others. So for example, if we see keratinous scales in the lizard, crocodile, and pigeon in the present day, but we don't see it in the perch or salamander or in the mouse or the chimpanzee, the logic is that these 3 species probably share an ancestor that first evolved keratinous scales, and that's an ancestor that is not shared by these other species. So the presence of keratinous scales in these 3 suggests that somewhere back in the past, they have a common ancestor that split away before any of these other lineages. Now, we don't know exactly what the relationship is among these 3, but we know that they're more closely related to one another than they are to any of these others. So the phylogeny, as we know, it looks something like this. This is the most logical state of affairs. So when you've got multiple species that share some novel character state that others don't have, the likeliest explanation is that those organisms with the novel character state belong together in a clade. Okay, there's one catch, and you may have noticed this already, but all you've got when you look at the present-day organisms is you've got the character states. You have some species without keratinous scales, and you've got some species with keratinous scales. Okay, so that's great, but what if keratinous scales aren't the novel character state? What if you started out with an ancestor that had keratinous scales and then some of the species lost it? Okay, that would imply that these species, the mouse, the chimpanzee, the fish, the salamander, the fish and the salamander, all these 4 right here are a clade, and these other 3 might not be. So you've got 2 character states, and some phylogenies even have more than 2 character states for a particular character. But there's only one of them that can be ancestral. Okay? So if you're going to define clades, if you're going to make the inference that organisms that share a derived character state belong together in a clade, if you're going to draw that inference, you need to know which of the 2 character states is derived. In other words, you need to know what's called the polarity of that character. The polarity of a character means which of the character states is ancestral and which character state or character states are derived. Okay, and you can't get this kind of information by just looking at the organisms that you've got. There's nothing in this group that is going to tell you which one of those character states is ancestral and which is derived. If you're lucky, you might, say, have a fossil that's found from somewhere way back here, and let's suppose that fossil, all the fossils you find way back here, vertebrates don't have keratinous scales, and you might be able to say, well, okay, I think probably that means that keratinous scales are derived rather than ancestral. But frequently, we don't have that kind of information. We certainly don't have that information when it comes to nucleotide sequences. And that's the most useful kind of phylogenetic information we've got these days, is genetic sequences. Fortunately, there is another way of inferring which of these character states is ancestral and which is derived. And the key is that, and maybe this is like, it's almost so obvious that I don't need to say it, but it's very important. The derived character state evolved somewhere in this in-group. It evolved at some point after the root of this tree. Okay, before this ancestor here, the derived character state presumably did not exist. So what you can do is, if the derived character state didn't exist before this root, if it doesn't exist outside of this in-group, you just look at some organisms that aren't within this in-group. You look at what's called an outgroup. If this outgroup all have keratinous scales, well, that suggests that that trait was around before this ancestor, this root, evolved. And if they all have keratinous scales, it stands to reason that probably this ancestor did too. In that case, keratinous scales are the ancestral trait, and the lack of keratinous scales is the derived trait. But if these organisms don't have those scales, that suggests that the presence of scales, is the derived trait. So what you do is you look at the outgroup. You look at some organisms that are close to but not within your in-group. And whatever character state they have, that's the ancestral character state. So for our vertebrates, what we can do is we can pull in this creature called the lamprey. It is a vertebrate, but it split away from the other vertebrates before any of these other organisms did. So it's a very good outgroup for this group. Turns out if you look at a lamprey, they are slimy and slippery, and they do not have keratinous scales. And so we know that the presence of keratinous scales suggests that these three species belong together in a clade. We've established the polarity of that character, and therefore we've established something about the evolutionary history of this group. So we're going to change our character state matrix now. We're going to add on the lamprey and all of its character states. And you'll notice something that's a little bit awkward here. Most of these characters, the lamprey has a no. It doesn't have mammary glands, it doesn't have claws or nails, it doesn't have fur, but it does have fins, and it does have gills. And this can get a little bit confusing, so probably what we want to do is swap the wording on this. We're going to change this to lack of fins and lack of gills. Okay, so that in each case we've named the character after the derived character state. This just saves some confusion, and you'll notice that the lamprey has a no in every case now. Just keeps things a little more straightforward. The way that character state matrices are usually filled out when you're looking at morphological characters, basically phenotypic characters you can see, is you put a minus sign for the ancestral character state, and assuming there's only one derived state, the notation used for that is a plus sign. So we changed the lamprey is going to have all minus signs by definition, since it's our outgroup. And then we just change all our yeses and nos to pluses and minuses.